So the section of the textbook that we looked at yesterday, a lot of it was about this thing called the short truth table method. And I didn't have you guys read that yesterday because it is not that useful for what we were doing yesterday, but it's very useful for the kind of stuff that we're going to be doing today in Unit 4. Now, a short truth table is not algorithmic in the way that the full truth table method is, meaning that even if you follow all the steps correctly, you're still not going to be exactly sure whether maybe you haven't found the right answer or whether the answer is not what you think it is maybe. So it'll become more obvious what I mean by that as we demonstrate this method. But it's an important thing to know about because it saves a lot of space. And because of the space that they take up to do, truth tables can become intractable very quickly. A five-line an argument with five different sentence letters in it that takes five different sentence letters to symbolize is going to take 32 lines on a sheet of paper. So that's about as big as you can go. An argument that would take six different sentence letters to symbolize would be 64 lines. It would take 64 rows to check, and so that's bigger than you can practically do on a sheet of paper. And that's not that complex of an argument when you think about it. So in order to evaluate these kinds of things, we need a different method. And if you want to do it by truth tables, you have to use the short truth table method. Right now, we're going to take a look at how to use short truth tables to check for consistency. So what we do is we make a single line of a truth table, and we don't fill anything out yet. Notice we haven't put anything over here on the left yet. So what are we doing? We're trying to make these true, and we use the information that we get from trying to make these true to fill this in. So this is a little bit easier to actually demonstrate than it is to talk about. Let's just take a look at how we would do this. So what do we need for P and Q to be true? Well, we need P to be true and Q to be true. Okay, so we need that in order to get this. So what does that tell us about this? Well, P is true, so this is true. And there we go, we're done. We've shown that set to be consistent, right? And we did that just by thinking about what it would take for this to be true. And we've shown that if this is true, then this must be true as well. So this set is consistent. Let's try a little bit tougher of an example. So that this method is ideal to use with sets of sentences that have conjunctions in them because there's only one way for a conjunction to be true. What about something like this? Okay, so first of all, we want to make P true, and that's probably the easiest. For P to be true, obviously P has to be true, so we put a T over here, right? We know that P has got to be true. What about not Q? Not Q can only be true one way. It's only true when Q is false, so we make Q false to make this true. Now what about P therefore Q? Well, that's false if these are true. But to make these true, P has got to be true and Q's got to be false. So this has to be false. It looks like there's no way we can make this consistent. Now, is that really like a proof? No. If you had to demonstrate this to somebody, you would have to fill out the whole truth table. And sometimes you're going to run into situations where this method is not applicable, where you can't figure out how to make these true, and you're not sure if it's because you haven't figured it out are because there really is no way to make them all true, and the set of sentences really is inconsistent. And in a case like that, you would have to just go ahead and do the full truth table. But this is a really convenient method for checking, even though it takes a little bit of reasoning about what you're doing. And as we're going to see next, it's really very applicable to the case of checking for validity.